Hello, in this short little video we'll talk about the vant Hoff and Clapeyron-Clausius equations. So first up, vant Hoff. And so this equation shows you how the value of an equilibrium constant, K, varies with temperature. And this is related to the enthalpy change of that reaction. And so you can have one equation, one reaction, as you change the temperature, you're going to change the equilibrium constant, which we know. We talked about this in the Le Chatelier's principle part, where if you have an endothermic reaction, it's like heat is a reactant. So if you add more heat by increasing temperature, then you're going to push the equilibrium to the right. Pushing the equilibrium to the right increases the equilibrium constant. And then the converse is true for if you have an exothermic reaction. Heat is a product. If you increase the temperature, it's like you're adding more of a product, and it pushes the reaction to the left, which decreases the equilibrium constant. All right, so these ideas are basically just put into this equation here. Your textbook derives it. I won't do that in a video because something tells me you might not want to see it, but definitely check out your textbook. This looks very, very similar to the Arrhenius equation that we saw in the mechanisms chapter. And it turns out that Van't Hoff proposed his ideas in 1884, and Arrhenius built on those ideas 5 years later and said, hey, since equilibrium constants involve rates forward and backwards, we can put rate constants here and activation energy in here and then use the same ideas. So they are kind of related. They look very much similar, just different letters in there. So make sure to keep them straight on your equation sheet later. Okay, so now from the Van't Hoff equation, we can get something useful. And not to say the Van't Hoff equation isn't useful in its own right, for sure. But from there, we can continue. So say we have this particular reaction. We have liquid water goes to gaseous water in equilibrium. So this is the equation that describes vapor pressure of a gas above its liquid. And at the moment, we're looking at water because we talk about water a lot. And so the equilibrium constant of this process is just equal to the either concentration of water or the pressure of water. And here we're doing Kp for pressure. And so, all right, because this is the gas, this is the only one that'll play into your equilibrium constant. And then we have the delta H for this particular reaction because we know the enthalpy of vaporization of water, and that's constant for all temperatures. So we basically plug this in. So we take K, we know what K is, and we plug it into here. And then we know that it's delta H vaporization instead of H reaction. And then now we get this form. And so this is called the Clapeyron-Clausius equation, or I learned it as the Clausius-Clapeyron equation, so it seems like there's some debate going on there. And so it just tells you how the vapor pressure depends on temperature. And we've seen these curves before. Oh, here's vapor pressure versus temperature. Yeah, it increases up to 1 atmosphere, where the vapor pressure equals the atmospheric pressure, and then it boils at 1 atmosphere, whatever. And so this is just giving us the equation of that line. And effectively, it has 3 components. You have one pair of vapor pressure and temperature, you have another, and then you have delta H vaporization. And so if I give you any 2 of these ideas, you can solve for the third. You can imagine solving for temperatures is going to be kind of a pain in the rear, so I probably won't make you do that on a test, but solving for HVAP and pressure is relatively straightforward, just some algebra. So let's practice that algebra. All right, so where do we start first? Always a good idea to see what you have and what you need to find. And so one thing that's implied in these problems is that you should know that normally at 1 atmosphere, which is 760 torr, water boils at exactly 100 degrees Celsius or 373.15 Kelvin. It's kind of an assumption, but it's a good assumption, so just make it. All right, so then in Denver, we have a second set of pressure and temperature. And so this is given as 630. Is hopefully 3 sig figs, but it might only be 2 sig figs, so I'm going to assume it's 2 through the rest of the problem. And then we're trying to find what this temperature is. I just told you I wouldn't make you solve for temperature on a test, and here we're solving for temperature. Well, we got more time, so let's do it. Then you have delta H vaporization and R, which you're going to need as well. All right, here we go. So now I'm going to plug these numbers in. Here's the pressures. Here's delta H vaporization. And then here's R. Now, you got to make sure the kilojoules and the kilojoules match, or the joules and the joules match. Somehow you have to solve this unit discrepancy between your enthalpy of vaporization and R. So here I just converted R into kilojoules, and we were set. All right, then here's the temperatures. Plug the numbers in, go to town. I didn't put units in here. Oops, I'll put them in next. And so then I'm going to solve the left side. I'm going to take this first term here and solve it. And then what am I going to do with the temperature term? Probably the easiest thing is to multiply both sides by the denominator here. And then you're left with T2 minus 373.15 on the right side. And now this is much more tractable to deal with. Then let me pop to a new page and rewrite this line. Alrighty. So now we can start fiddling with this. If you multiply the two numbers on the left side, you get negative 70 Kelvin. You distribute the 4906 into this parentheses on the right, and you get these numbers. Kelvin squared, that's a weird unit, but it works out here in the end. And then I'm going to subtract both sides by the Kelvin squared. Actually, I shouldn't say that. I'm going to add Kelvin squared to both sides. And then I'm going to add 70 Kelvin times T2 to both sides. And so effectively swap what's on the left and on the right. And so 4906 plus the 70 gives me 4976. And then now I can divide both sides by 4976, and I get the answer in Kelvin. I'm going to put it into Celsius. And remember, we got 2 sig figs, so that's going to limit some things. All right, so 367.9 Kelvin minus 273.15. Great, this gets us into 95 Celsius is our answer. So the boiling point of water in Denver, which is a mile high, is lower than at sea level. And so this is why, say, you might need high altitude directions for the things you cook, because your water and baking and anything else you're cooking is going to be at a lower temperature. Great, that's all I have for now. Thanks for watching.